Question 21. A body falls freely with negligible air resistance. What quantity of the body is its rate of change of momentum? Well, rate of change of momentum, the definition of rate of change of momentum is force. So which one of these is a force? Not a force, not a force, not a force. Weight is a force. So that's a force. So it's that one. A firework rocket is fired vertically into the air and explodes at its highest point. What are the changes to the total kinetic energy of the rocket and the total momentum of the rocket as a result of an explosion? Okay, so when it's reached its highest point, here it goes, whee, like that, it's just about to turn around and fall back down again. So at that point, instantaneously, its speed is equal to 0. So its kinetic energy just before it explodes is 0. When all the bits fly off, then they've clearly got kinetic energy. So the kinetic energy has to have increased. It's gone from 0 to something. The total momentum of the rocket, well, in the instant of the explosion, no external force has had a chance to act. So therefore, by conservation of momentum, it must be unchanged. So momentum's conserved means it must be unchanged. That goes up. So it's like that. Now the momentum will increase over time because gravity will have a chance to act, and that's an external force. A lift and its passengers with total mass of 500 kilograms, write it on the diagram, accelerates upwards at 2 meters per second squared. 2 meters per second squared. As shown, assume that gravity is 10 meters per second squared. What's the tension in the cable? Well, we need to find the, use Newton's laws here. So we have, let's write down this force here. So the weight of the object will be mg. So Newton's laws is that F is equal to ma. F there is the resultant force. So that's T minus mg is equal to ma. So that is T is equal to ma plus mg is equal to 500 times by the acceleration 2 plus the weight, which is 500 times by 10. So that's 5,000 plus 1,000 is equal to 6,000, which is that one. Which of the following is not a unit of power? Well, these are can be quite tricky, so we have to work our way through it. So Newton meter per second. Well, a Newton meter, so power, sorry, is equal to the energy divided by the time, isn't it? So a Newton meter is a unit for energy and a second is a unit for time, so that one is a kilogram meter squared per second to the minus 3. Okay, B, kilogram meter squared per second to the minus 3. Right, well, a Newton is equal in units to a kilogram meter, kilogram meter per second squared. Right, if we want to turn that into an energy, we need to times by another meter, because work done is equal to force times by distance. So we times by another distance there. If we want to turn that into a power, we need to divide by another time. So that one, so we've got kilogram meters squared over second to the minus 3, so that one is a unit of power. A joule per second, yep, that is a unit of power, so it must be this one by process of elimination. Car accelerates uniformly from rest along a straight road. Which graph shows the variation of displacement with the car speed? Well, you should know it looks like that, but let us see why. So S is equal to ut plus a half a t squared. So it's uniform from rest, so that's 0. So S is equal to a half a t squared. It says the acceleration is constant, accelerates uniformly, So it's got to be a t-squared shaped graph, so it's that one. Okay. Question 26. Which of the following statements is correct? Force acting on an object is equivalent to, well, force definition, Newton's law, mv divided by t, rate of change of momentum. So the change in momentum, that's false, because it's the rate of change of momentum. I'll just skip across to C first. The energy it gains per second, no, that's power, so that's false. The acceleration per meter, no, God knows what that is, that's false. So the impulse it receives per second, right, let's think about this a little bit. So change in momentum is exactly the same as impulse. So therefore we have impulse divided by time. So it is the impulse it receives per second. So it's that one. Okay, so 27. A load of 3.0 newtons is attached to a spring of negligible mass and a spring constant of 15 newtons per meter. So first thing we need to do is to use Hooke's law, which is like that. Rearrange it and we get delta L is equal to F over K, which is going to equal 3.0 divided by 15, which is equal to 0.2 meters. And then we need the energy stored in a spring. The energy stored in the spring is that expression there. So the energy is equal to a half F delta L. It's equal to a half times by F, which was 3 newtons, times by 0.2 meters, which is going to equal, that comes to 0.3 joules, which is that one there. Question 28. A diagram shows how the stress with strain varies for specimens X and Y, which are different. Both specimens were stretched until they broke. Right, which of the following is incorrect? Okay, X is stiffer than Y. Well, it's got a steeper graph, means it's got a higher Young's modulus, so that is true. X is stiffer than Y. X has a higher value of the Young's modulus, yes, because it's a steeper graph, so that is true. X is more brittle than Y. Well, they both virtually break at the same strain, so let's come back to that one, shall we? Y has a lower maximum tensile stress than X. Well, there's Y's maximum tensile stress, there's X's maximum tensile stress, so that one's definitely true. So X is more brittle than Y, not really, they're both about sort of the same. So that one must be false. Okay, 3 identical cells of internal resistance R are connected in series with an external resistance of R. The current in the external resistor is I. If one of the cells is reversed in the circuit, what's the new current in the external resistance? So this is relatively easy. So we've got 3 cells. So, and we have an external resistance of R like that. So if we have them like that, and this is 3V, because there's 3 whatever the voltage is of the cells, then we drive a current of I around. Now, if we switch the cell, one of the cells around, so we've got this, instead, well, we're still going to have 3R of internal resistance, but that cell and that cell, their EMFs are going to cancel each other out. So the voltage that will develop will be 1/3 of the value that it was there. I is equal to V over R, which means that the total resistance is exactly the same. We've got the internal resistance of 3 and the external resistance of 1. So that's going to be exactly the same. So if the voltage is dropped to 1/3, then the current will drop to 1/3. So it's got to be 1/3 of I. Question 30. In a cathode ray tube, many electrons strike the screen in 40 seconds. What current does this represent? Well, current I is equal to Q over D. So therefore we have the charge, which is that many electrons, 7.5 times 10 to the 15, times by the value of each electron, 1.6 times 10 to the minus 19. And we need to divide that by the time, which is 40 seconds. So we have to do that on our calculator. So here goes. Right, 7.5 times 10 to the 15 times by 1.6 times 10 to the minus 19 divided by 40. So this is this one here, C. A cylindrical conductor of length L, diameter D, and resistivity ρ has a resistance of R. What is the resistance of another cylinder conductor of length L? So length has stayed the same, the diameter has halved, and the resistivity has stayed the same. Okay, so R is equal to ρ L divided by A, which means that R is proportional to ρ L over, well, A is proportional to the diameter squared. So that means that the resistance depends inversely on the diameter squared. So R2 will equal ρ L over the new diameter, which is d over 2 squared. So that's the old values. So that's the same, that's the same. The diameter has halved, which means that you have ρ times by 1L over d1 squared. That's the original resistance. And we also have a quarter coming out here, like so. If we divide by a quarter, that's the same as timesing by 4. So we got 4, and all of that is our original resistance, R1. So it's 4R. Right, so this may be a little bit confusing, but what do you need to do? You need to identify the main equation here, how the variable that you've got that's changing there is affected. So because it's a d squared here, essentially if you divide that by 2, when you square it, you're dividing the area by 4. Because area is on the bottom, that increases that by 4. If that reduces by 4 times, that increases by 4 times and makes that bigger, because you're dividing by a smaller number. Right, question 32. The cell in circuit has an EMF of 2.0 volts. Write all your information that you get onto the diagram straight away. When the variable resistor has a resistance of 4 ohms, the potential difference across the terminals of the cell is 1 volt. So, right, we need to put in here an internal resistance, don't we? And then we can say that the voltage here across the terminals is what? 1.0 volts. Okay. What is the PD across the terminals of the cell when the resistance of the variable resistor is 12 ohms? Okay, well, first of all, let's work out what the internal resistance is. So I is equal to V over R. Well, that's going to equal, there's 1 volt across this 4 ohm resistor here. So 1 volt across 4 ohms there. So I is equal to 0.25 amps, which means that R is equal to V over I, which is equal to 1 volt. It's 1 volt across that, divided by 0.25 is equal to 4 ohms. So the internal resistance is 4 ohms. Right. that will always get you there, but you can see a shortcut here. The PD across the terminals is half the EMF, and if it's half the lost volts here is half the potential, the voltage across here is half the potential. So if you've got 2 volts, so you'll have 1 volt across here, 1 volt across here, which means that these 2 resistors must be the same. So there is a shortcut, you can just say that that's 4 ohms. Right, let's work it out for the new arrangement. So we have 2.0 volts there, we have 4 ohms there, we have 12 ohms there, and we need to work out the voltage across the terminals of the cell. That's the voltage across there. So what do we do? Well, let's work out the current first. So I is equal to V over R, which is equal to, there's 2 volts in total, divided by the total resistance is 4 plus 12 is 16, so that's 0.125 amps. And then we do V is equal to I times by R, which is going to equal 12, the resistance there, times by the current 0.125, which is equal to 1.5 volts, which is that one. Now there's an easy way to do that as well. That's 3 times bigger than that, so that one must have 3 times as many volts across it as the lost volts on the internal resistance there. So if you want to divide 2.0 up in 3 shares and 1 share, then that's got to be 1.5, that's got to be 0.5. Okay, right. Question 33. The graph shows the current voltage characteristic of a filament lamp. What's the resistance of the lamp when the potential difference across the lamp is 4 volts? So we need to go up to there, like so. Draw our line across like that. And it looks like that's 8. And be careful, the units there, milliamps. So we've got R is equal to V over I, which is equal to 4 divided by 8 times 10 to the minus 3, which is equal to 500, I think. Let's just check it. 4 divided by 8 times 10 to the minus 3 is 500. Right, and the last question. Which graph shows the resistance per unit length of a wire, how it depends on its diameter? So remember, we did it up here. The resistance is proportional to R, L over D squared. Well, the resistance per unit length is R over L. It's proportional to R over D squared. That's a constant. That's the resistance per unit length. So we need a graph of 1 over D squared. The only graph of 1 over D squared looks like that one there. So it's D, like so. Done. Okay, well, thanks for watching. I hope you found this useful. If you did, then please tell your friends about it. You can comment in the section below and I'll try and answer any questions that you have. And I'll be releasing more papers soon, so subscribe to the channel to find out when new releases are. Thank you.